Welcome to qnawire.
This problem, we have a fairly complicated steam plant here, power plant. Turbine, boiler, condenser as normal. A pump here that this is an open water, an open feed water heater. So we need to pump up the pressure from out of the condenser so that it is the same as the pressure coming down from 10. So the pressure at 2 and at 10 are going to be the same, and the pressure at 3 and 2, and then well, here we have another pump. So then we're mixing here. We're mixing steam from the turbine, feed water, and then the steam from the turbine that has been cooled in a closed feed water heater here. So this pump pumps it up to the boiler pressure and feeds it in here. So we have a kind of this complicated TS diagram where we have, let's see here, we have a feed coming off at 9, at 10, and then 11 is the exit. Up at the entrance, we have 10 megapascals. The first feed here is coming off at 1.2 megapascals, coming off here at 600 kilopascals. So then we go through the pump here, and here I think we have a saturated vapor at 3, at 1, and at 7. No, I think that should be a 6, not a 7. That can't be right. That's going to be a 6. So here. And let's see here. We know the temperature. Do we know the temperature at the turbine? Yeah, that we normally need that to make any progress. So the temperature at 8 into the turbine is 600 degrees Celsius out of the boiler and into the turbine. Okay, so got a lot to analyze here. Let's start with this pump. We can give the enthalpy as condensed saturated liquid here, the specific volume, and then we can get the work done by this pump in pumping it up from 10 kilopascals to 600. So we get very little specific work into this pump. Let's see here. Then we have we can then find the enthalpy at 2 because that's this plus this. And now we can look at 3 because let's see here. 3 we know the pressure at 3, and we know what else do we know at 3? The pressure at 3. Oh, and it's a saturated liquid. So we can get this information at 3 here, the enthalpy, the specific volume, and that means we can figure out the work done in going from 3 to 4 by the pump, and that's about 10.4 kilojoules per kilogram. And then we can get the enthalpy at 4, which is enthalpy at 3 plus the work done by the pump. And now we can turn our attention to 6. So 6, we have pressure and saturated liquid. So we can get our enthalpy. We can figure out what our temperature is there. And we know that the temperature at 6, at 5, temperature at 6 right here is also going to be the temperature at 5. Okay, yeah, so we're assuming again that we have an ideal heat exchanger. So what's coming out here is also the same temperature as what's coming in here. So we got a good heat exchange in there. So then we can get the enthalpy at 5 because we know the pressure and the temperature now at 5. This is not the enthalpy at 6, is it? What is this? What is that? Did I? 6? We knew the enthalpy at 4. And so at 6, we have a pressure and we have a we have a pressure and we have this. So that we got. So then what is this? Where did I, what did I write wrong there? That's got to be, that can't be 6. That can't be a set. That has to be, that's too high of a, is that 8? That might be 8. Let me check my notes, because that's too high for a liquid. Much, much too high for a liquid. So let's see here. I bet you this should be 8. I'm almost positive that that should be 8. Let's see here. 51. Okay, let's see here. An enthalpy of 36. Where did I get that? 6. Oh no, I'm looking at the wrong problem again. 53. Yes, enthalpy at 8. Yes, indeed. That should be an 8, and that should be an 8. 8, and fix my H, and then that should be an 8, and fix my 9. All right, so there we go. That makes a lot more sense. So this is the enthalpy going into the turbine and the entropy going into the turbine. We also know, so we know the entropy at 8 is the same as the entropy at 9. Why did I write this? Should be an 8. Right here should be an 8, obviously. All of these are the same. So we have, let's see here now. Where are we at? So we know the enthalpy at 9, and we know the pressure at 9. So we know the entropy at 9 is the same as the entropy at 8. So we know the pressure at 9. So we can get the enthalpy at 9. Likewise, we can get the enthalpy at 10. Likewise, we can get the quality factor at 11 and the enthalpy at 11. And so if we look at this is the, let's see here, 8, 9, and 6. So this is the closed feedwater heater, mass energy balance, and then we've also used the mass balance going through there. Defining y is m.10 over m.5. We get an equation for y here, and then we get y is about 5.4%. So we're taking about 5.4% off of, wait a minute. This is, let's see here. This is a complicated problem. So let me see here. Y is 10. So this would be the feedwater heaters. This has to be 5 and 9. 9 and 5. Yeah, that's right. So this should be a 9. That should definitely be a 9. Yep, that's right. Yeah, that should be a 9. That should be this. Oops, this guy. So then we have, we do an enthalpy balance on the mixing here, the open one. And so we define Z as the percentage coming off of here. And so Z is m.10 over m.9. No. Yeah. So that's in this closed one. So we have all of these enthalpies going in and then the enthalpy coming out. So we know the mass flow rates here all have to add up to the mass flow rate there. So we gotta use conservation of mass too. And so that gives us an equation for Z, which is Z is M dot 10 over M dot, what were we using to 5? So we get an equation here for, we know everything in this equation except Z, so we can get Z is about 17%. So we're taking another 17% off of there. And so now we have our enthalpies everywhere. And so now we can get our heat transfer in the boiler, the heat transfer out in the condenser. So we have, again, not everything flowing through the condenser. So we're siphoning off some portion of the mass that's going through the condenser. So we need to take account of that. And then we can find the net work is this minus this. They told us that this was generating 400 megawatts. So we can figure out the flow rate is 313 kilograms per second. And finally, we can take this and divide it by this, and we get 45.2%.